Swayam Prabha. Digital India. Educated India.
Combustion mainly consists.
No, he has also written combustion, so I by mistake
What he wrote? I welcome you to this online discussion forum. I received a couple of questions. One is, can you guide how can we relate Poiseuille's equation and Darcy's law? Can we obtain expression of permeability by relating them? It will be very helpful if you can guide with numerical problem. Okay, basically Poiseuille's equation and Darcy's law. Now, what I have here in front of me, this on the slide here, you can see that this is here that we are, you can see here that this is the equation which you end up based on Poiseuille's equation. Okay, so this is our we have gone into this mode of Kozeny-Kármán equation, or finally the Ergun equation format. Now, in this format, you have see this is the velocity, superficial velocity. We have here VO squared term and VO term, and delta P by L is the pressure gradient. So here this VO we have, it is basically VO. We get it VO as a function of delta P by L, which is the same thing as what we saw in case of Darcy's law. There also the superficial velocity is related to the pressure gradient. Only thing is the functionality is completely different. There we just used a single lumped parameter which you referred as permeability. Here we don't have a lumped parameter. Here first of all we have a quadratic equation, you can see, with V naught square, V naught, and you have so many other parameters. dP is the diameter of the particle that is constituting that porous medium. Psi is the void fraction. So you have phi s is the sphericity factor. So you have so many other terms. You have density coming in. So you have so many terms. So this is a more comprehensive expression of superficial velocity as a function of pressure drop. And the Darcy's law is a more simplified expression. I don't think you can get permeability as such out of these expression. I mean that's not the idea by which this whole equation has been floated. So I think these are two different equations. Darcy's law is a simplified form, and this is a more exhaustive form, and this is more applicable, I think, for a packed bed. When you know the particle diameter, when you know all these parameters, you know. But when you do not have that, you are just treating the porous medium as a black box. There only the permeability term as a lumped parameter is taking care of these all these nuances. So these are completely two different approaches, and there is no point in finding permeability out of this expression as such. That would be the answer in this case. And you have another sentence. It will be very helpful if you can guide with numerical problem. I think in the assignment I have given you a certain number of numerical problems, and in fact down the line you will have more number of numerical problems. In fact, in some assignment sets it would be all numerical problems, you will soon find. So there will not be any dearth of numerical problems, and as such in this course I think the concepts are extremely important. You need to find out the dependence of different parameters. So, but down the line, wherever the numerical problem is required, for example, for design of a system and all, you will be given those kind of assignments down the line. Okay, that is as far as the first question is concerned. Second is, can you suggest me a reference book which mainly consists combustion through porous media? Now you are interested in combustion through porous media. We have down the line in later lectures you will find there is a lecture, there would be one module on heat transport through porous medium. Okay, so if there is a heat transfer process going on, then if the porous medium, the solid material has a thermal conductivity, then how the heat front progresses. So the progression of heat front in a porous medium, that we will discuss in detail in subsequent lectures, which has not come, which is in the later part of this course. There you will get ample opportunity to see how progression of heat front is accounted. And if you want to have a combustion in that case there would be a generation term. Combustion means heat is getting generated through some reaction. So there would be additionally one reaction term coming in that movement of combustion front. So the best part of it would be, I will be able to discuss this how the reaction term will come in. I think you will be able to figure it out yourself by the time when we go to this thermal front, because that would be just near the end of this course. So at that time, if this question still persists, we will try to address this in the online similar discussion forum at the end of the course. But first you go through this course material, and particularly the progression of the thermal front. Once you do that, and before that itself you will know how we account for the reaction term. Okay, so when you have this progression of heat through porous medium, there you have to only have a generation term when you have combustion. So that can be accounted easily. But I think I should be able to I'll be able to discuss that only after you go through that particular module of progression of heat front through porous medium. Okay, and you are asking me to suggest a reference book which mainly consists combustion through porous media. I am not. There is a classical paper by Bailey Larkin where they have Bailey and Larkin. That paper gives you this entire these theories of I think underground gasification. They have given a very good example of this combustion inside a porous medium. That paper is by Bailey and Larkin. I do not have exactly the full reference, but I would definitely, by the time this next or what you can do is, if you when this discussion comes up, when this progression of thermal front, when that lecture is when that is open for discussion, at that time you put this question in the forum, that full reference of Bailey and Larkin. That time I'll give you the full bibliographic reference. That I can do. I do not recall as such any book immediately on combustion through porous medium. I cannot recall right at this time a book on this. Bailey Larkin's that paper is a good reference for combustion in porous medium. Yes. Can I see directly from the laptop? Can I not?
No, sir. The questions are not there yet. They have told that if the question is not coming, if the students does not have any questions, then you can just discuss about this course for 15 minutes. Then we can stop it.
Achha, no. What is this point here? Oh, okay.
The question is not there. It is already connected.
See, there is a question some time back we received which says for the formula of porosity, you have assumed porous medium is completely homogeneous. So, what do you mean by that? As in your given example, you take height of conduit is 3 meter. So, we can visualize and agree that pressure within conduit would not be of much difference. But in reality, oil wells have height of approximately 120 feet. I think we can consider this 2D approximation in this. We cannot consider. No, what I did not quite understand is this 3 meter. Why we are having the flow? We are having the flow only over the pay zone. I mean, if you are looking at oil well, for example, it is only the pay zone that is that height we are referring to. First of all, so if I look at a fresh page, for example. If we try to open a fresh page, or I will since I am not getting it, so let me use this part here. What we are looking at is a oil well. When we have a oil well like this, then we have the pay zone is here. This may be the surface, and this is the well. But the pay zone thickness is this much. So, you have this is the pay zone thickness over which you are having the flow, either inward flow to the well or outward flow from the well. So, this is this thickness, and this thickness is not much. I mean, you cannot take these entire, we are not solving for this entire height, we are only solving the flow only for this part, okay, through which the flow is taking place, number one. Number two, if you are looking at the z axis in the well, in this axis, if you look at this part, this is actually open conduit. So, the flow resistance would be minimal, whereas when it comes to porous medium, the flow resistance would be much higher. You must agree to it. I mean, having a flow through a pipe and having a flow through a porous solid, these two are completely different things. So, the pressure drop over this length, for any flow to take place, the pressure drop over this length, this would be much smaller compared to if you go even this distance in the porous medium. So, that is why this pressure drop can always be neglected. Pressure drop through the conduit over that 2 meters or whatever meters distance you have, which is known as the pay zone. So, that is the only thing that is assumed, and which is, I think, fair enough. I mean, of course, you should go for a 3-dimensional simulation because of this reason that your permeability will be varying over this thickness. So, you cannot consider single permeability over this entire thickness. So, for other reasons you may have to go for 3-dimensional considerations. But the reason that you have given that here would be a pressure, there would be a pressure drop, I don't think that is any reason, because here it is a pipe. A pipe means the well, and well has there is hardly any resistance for a fluid to flow through this large diameter pipe, as against flow through the porous medium. It would be the pressure drop would be much higher, flow resistance would be much higher. So, that would be controlling, and that is taken care by the radial velocity and the radial component, etc. So, if at all you go for a 3D simulation, that is for some other purpose. That purpose would be you have a permeability variation in z direction. For this reason, I don't think it would be, this could be a very major reason for which you go for 3-dimensional one, and you must appreciate the simplicity that you have brought in by considering the 2-dimensional flow, which was not possible in case of 3-dimensional flow, because 3-dimensional flow you have to completely rely on a numerical simulation, whereas for 2-dimensional flow a lot of analytical solutions were generated, and those analytical solutions you can visualize by looking at those expressions. So, that you must take into account. Okay. The other question that you have is, I have a question regarding Taylor series. Why does the expansion happens over length and how? which Taylor series expansion you are referring, and which lecture? That has to be understood. Taylor series, why does the expansion happens over length and how? First of all, I do not understand which equation you are referring, where we did this Taylor series expansion, but if at all I have done it, if it is done over length, that means we must be doing it for a differential for a differential element. We constructed a cube, we constructed a differential volume of dimensions delta x, delta y, delta z, and since this delta x is small, so we can assume, let us say I'm looking at the variation of pressure within this differential volume. So if we look at the variation of pressure within this differential volume, so then pressure would change from left face of this differential volume to the right face. So we can, instead of treating the pressure as it is, we can linearize within this distance. Within this volume, we can assume that the pressure in the x-axis.
Continuation. He's asking about this friction factor.
For friction factor, we have done Taylor series expansion. Let me see what it is. Friction factor I do not have. This is the friction factor. Then we have this. I don't see where we have used friction Taylor series expansion in friction factor. No, I don't see where we have used friction Taylor series expansion in friction factor. No, I don't know. I do not see where I have used Taylor series expansion in friction factor. Taylor series expansion, if I had taken anywhere with respect to distance, that is there, and then we only considered first order term and ignored the higher order term, that means that the pressure is linear within these differential element. It is changing linearly with x, linearly with y, linearly with z. So that is why only we are taking first order term and we are not considering the higher order terms. And assuming only the linear term, that means our differential volume is very small. Even if there are contribution from the quadratic contribution from higher order terms, that would be negligible. But if your differential volume is larger, then definitely you have to consider the higher order terms. That's the idea. But in case of friction factor, I don't think I have used this Taylor series expansion. किसको क्लिक करें? Number 1 from the left. Select pen, then first icon. Okay, thank you. See this. There is a question on this how this Dirac function is applicable in case of a miscible displacement. What we do in case of a Dirac function, what that means is for a miscible displacement we are looking at a spot of dye is placed in a infinite medium. So that means this is the infinite medium. Let us say this is the axis. This is the axis. So this is what is z. So this is tending to plus infinity and this is tending to minus infinity. So Dirac function is basically at initial state you are putting a spot of color in an infinite medium. So at t equal to 0 the concentration of color is 0 everywhere and the concentration of color is infinity at z equal to 0, and again it is 0 everywhere when z is greater than 0. So this is a Dirac function, classical Dirac function, and this simulates a spot of dye in an infinite medium, spot of tracer, spot of color in infinite medium. And the idea is that as time progresses we will see that there would be a build-up of concentration in the surrounding medium and there would be a reduction in concentration in the concentration at z equal to 0. So at time t equal to 0 that entire solute which is m gram of solute, that m gram of solute is condensed within a 0 volume at z equal to 0. So that is why the concentration has become infinite at that time, and then as time progresses that m amount of solute gradually occupies the entire medium. So that is something which we are trying to solve. So what we did is we have taken a differential element at z and we had done we have seen how much of flux is going in from left face, how much of flux is going from the right face. We are working only with the right half, treating this as a symmetric half. So we are working only from z equal to 0 to z equal to infinity. So we picked up a differential element, we found out how much of flux is going from the left end and how much of flux is leaving from the right end, and these difference will give you the accumulation in that place. And if you do that, this I think I have talked about earlier also if you go through the video lecture we had a detailed discussion on this. If you equate these two and with the accumulation will take place if we have area A perpendicular to the screen. So area A multiplied by this distance delta z, this distance is delta z. So this distance delta z means the volume is A delta z. So A delta z volume means A delta z into rho would be the mass. Okay, so similarly you can or A delta z is the volume, if C is the concentration then A delta z C would be the concentration of solute inside this differential volume. So then flux from left hand side minus flux from right hand side is equal to accumulation in this volume. So if you do this you will end up with fixed second law which is del C del T is equal to d del square C del Z square. That equation you will end up with, and then we put these initial and boundary conditions. That means at t greater than 0 we write at t greater than 0 when you go to C at infinity concentration never reached, the concentration will never increase, concentration will remain at 0. So this is one boundary one boundary condition. Another condition is that anytime the total mass of solute that is present in the system, total mass of solute means the total mass of solute is m, that is present in 0 volume at time t equal to 0, and that is now spreading. So at any time it would be concentration of solute multiplied by A dz. A dz is the volume over which this concentration is applicable. So concentration kg per meter cube, A is meter square, dz is a meter. So kg per meter cube into meter square into meter. So this is kg, then meter cube and meter cube will cancel out. So these kg for all such differential elements. So that when you do integration from minus infinity to plus infinity, that should give you m. M is the total amount of solute present, and this will follow directly from the Dirac function, because if you put these because the spot of tracer, the Dirac function says C1 would be equal to m by a delta z, where delta z is the Dirac function, and the property of the Dirac function is integration of delta z dz minus infinity to plus infinity, that is equal to 1. So that's how the property of Dirac function works. So that is why you can use this. So you can see this automatically follows that at any time in this diffusion process, the total mass present in the system is m, which you placed in the beginning. So this is essentially this is the use of Dirac delta function, and this is how this whole thing works out. And then this was solved, and you got the solution which we discussed down the line. So is this all right? I mean, this is you asked me to basically explain the you asked me to explain the Dirac function once again in case of miscible displacement. Yes, and so that is what is done. Yes, that is all I can think of as far as the answer is concerned. Sir, can you explain the hoga? And then, sir, how is the Dirac function used in practical purposes, especially in oil and gas exploration or production? No, you can do tracer tests. You can always do tracer tests. Suppose you want to know that you want to characterize a reservoir, so you want to perform a tracer test. So naturally, we are going to talk. I mean, in this course, we are talking about two types of tracer tests. One is where you give this Dirac function. That means you give a short pulse, or you can give a step change and see how that step change travels. Now, if you are doing a step change in a large reservoir, you can see that would be very. I mean, that would require a lot of tracer, because initially it was zero concentration and then you continue to inject tracer for some time. So always you would be going for a pulse. That would be easier. I mean, you are having water injection. So instead of water injection, for a short time you give a pulse of a tracer. So then you try to see where all it appears at when it appears at the production end, that pulse, and so that pulse, how much that pulse is broadened. I mean, so basically it is even in reservoir scale, or when it comes to doing it in a core flooding experiment, there you can give a pulse and see how much it is getting broadened, and from there you will get an idea what is the dispersion coefficient. And that is I mean, if you have a large dispersion coefficient, or if you have how is your dispersion coefficient, and how that compares with the bulk diffusivity. From there you can get some feel, okay, whether the porous medium is homogeneous or it's highly heterogeneous. So that is applicable in reservoir scale as well as in the core flooding experiment. So I think that in fact this is a very important tool. These tracer tests are a very important tool for reservoir, I mean for oil and gas reservoir applications. Your question is, why does dispersion coefficient and concentration decreases if diffusion coefficient increases? I do not understand what you mean by concentration decreases. This part is not clear. Whose concentration you are talking about? And why does dispersion coefficient decreases if diffusion coefficient increases? Dispersion coefficient, if you are looking at dispersion in a capillary where you are having a parabolic velocity profile, there we have already seen that when you have a parabolic velocity profile, then you have, suppose I have given a pulse, that pulse is now stretched in the form of a parabola. Had it been a plug flow, the pulse would have been simply appearing like a straight like this. So instead of that, this has been stretched like a in the form of a parabola. So then in this case, you have now the diffusion can take place like this. Diffusion can take place over a large band. Here in this case, diffusion was taking place a little bit through the sides, and so over this band the diffusion was taking place. But here, because this pulse has been because this strip has been stretched in the form of a parabola, the diffusion is happening over this entire zone. Now, if the diffusion is, when the diffusion, your question is, in the formula, that concentration written as C1 bar, I mean tailored dispersion formula. Okay, I will get to that in a moment. Let me complete this exercise. What was the earlier question? Dispersion coefficient decreases if diffusion coefficient increases. So if diffusion coefficient increases, that means, let us say this, you start stretching this parabola. So as it travels, it goes further, it stretches down the line. But then if your diffusion is slow, if the diffusion is slow, then truly you can stretch this strip all the way here, and then when you collect this entire material at the outlet, then you are picking this slice like this, and then you are mixing it in a mixing cup and finding out what is the average concentration, and that concentration you are plotting. So you can see when you after you collect it in the cup, you will be getting a mixing zone which is this big. Okay, but whereas when the diffusion is fast, this is where slow diffusion, you allow this parabola to form with this strip size remaining as it is. Whereas when the diffusion is high, then this strip will not maintain it as a strip, because of diffusion this will all mix and form a band. Okay, so then you are again coming close to this situation. Okay, so when your strip is maintaining its form as a strip, then it will continue to expand like a parabola, and you are creating a much larger mixing zone. So when diffusion coefficient is less, essentially you are having a larger dispersion, because at the end of the day you are collecting it in slices from the sides, and these slices, as I said, these slices are mixed and you are getting this concentration. So as if your mixing is over this entire length. But this will not be possible if your diffusion is very fast, because then everything would be then all mixed up, and they are forming a band here itself. So that you will not be able to maintain the strip as it is and stretch it like this. So this you can think in this line, that why dispersion coefficient is inversely related to diffusion coefficient. And regarding your concentration increasing, let me see. Concentration increasing is, this is the C1 bar. Where did I use C1 bar? This is C1. Okay, this is just simple C1. C1 bar is here. C1 bar is a function of the concentration decreases. I'm still not quite convinced. I mean, you must understand the effect of why dispersion coefficient, how it relates to. I mean, when you have when you have a when you have a solute which has large diffusion coefficient, then what would be the scenario of dispersion? That we need to understand intuitively. And then if we understand that, this is basically, this is what is you have as a C1 bar. This is the expression. What you mean by C1 bar increasing is not fully clear to me, but this is what I. Okay, so this is what I can think of at this time. Okay. Thank you all whoever attending, the students. I hope you are having a good session. I have with me two of my assistants here. One is Shruti. He is behind the laptop and he is helping me with all these questions. And I have Arindam Banerjee, who is also playing he is also playing a major role here. So they are basically with me for this online session, and they are the TAs who are. There is another gentleman, Madhav Chauban, he is also there, and they are primarily answering your queries. And so I hope you will have a good session and good learning experience. Let's see, we will have this kind of online sessions again as per the provisions of this course. Thank you very much. That's all for today.